Your textbook has some nice type of problems where you have to find the area of something inscribed inside particular graph. I kind of like those problems, so I made up this one, and I just decided to describe it in words, although I don't expect you right now to know what this graph looks like, so I'll do that for you. Anyway, the base of a rectangle lies on the x-axis, and its right side lies on x equals 2. And do you know what that is? X equals 2 is a vertical line. It's where all the points where x equals 2. The upper left corner touches the graph of this exponential function y equals 2 to the x power. We're going to study these in the last chapter, those types of functions. Write the function describing area of the rectangle in terms of x. Alright, now once you see the picture, it's going to start to become a lot clearer what I'm talking about, so let's go ahead and draw it. And this exponential function, I'll give that to you, it goes like this. So here is y equals 2 to the x power. Alright, exponential functions are flat at one end, where they level off at an asymptote, and then they continue to rise and rise and rise, and at the other end. Alright, now at 2, x equals to 2 is a vertical line. And so a rectangle, which I'll do in black here, is going to have to look something like this. If I have described this right, and I think I have. The base lies on the x-axis. The right side lies on this vertical line, x equals to 2. And the upper left corner lies on this graph, y equals 2 to the x. Alright, now, as a matter of fact, what is this point here? Well, if I say, well, this is x comma y, it's a coordinate, that means that that point there is x, isn't it? Alright, I hope that's big enough to see on your screen. So this tells me the base of my rectangle. If I go over x units to here to get to this left-hand side of the rectangle, over here somewhere, I'll call it x, then this distance would be 2 minus x, wouldn't it? So this is 2 minus x. And the height is y. So I can provisionally write down the area. The area would be length times, or base times height, 2 minus x times y. But that's not a function of a single variable x. So how am I going to get rid of y here? Well, the very act of being positioned on this curve means that this y value has to obey this function, y equals 2 to the x. So the area would be a of x, if I call it that, would be the 2 minus x, and then y, I'm going to substitute my function, 2 to the x power, times 2 to the x. So there we are, and that's my function. So what was the deal there? Well, again, we had to eliminate one of these variables. We had to eliminate y in this case, and I found a way to describe y, because the constraint in this problem, and you think of these as constraints, the constraint in this problem is that this rectangle has to lie along this curve. And what it does, it means the y value, which is the height, has to obey this function. It has to be the same as 2 to the x, whatever the x value is. And here's x. So that gave us that function there. Alright, so now we can ask that. The other interesting question, of course, is what is the largest rectangle you can make under this circumstance? And that's a great question. I don't know. It would require methods of calculus to figure that out. But we've made the step of treating this as a math modeling problem and creating the function. So now we are ready to take that next step once you learn a little bit of calculus.